so now we're going to talk about measurements. Measurements are just clutch, very important in terms of any science endeavor, any business endeavor, any science endeavor, anything where you're going to be making quantifiable claims, right? So we need to talk about measurements. Now, every measurement has got three parts. Where's my pen? It's got number one, a number, number two, a unit, and these are where most people stop, okay? It turns out, though, in physical sciences, we are going to need to be talking about the uncertainty of a measurement, right? So we'll talk more about that in a minute. But a number and a unit are the biggest parts, and you'll get a lot if you just understand those two things, a lot, all right? So number one, units. Without units, a number can be meaningless or confusing. In chemistry, we use an updated version of the metric system known as the International System, or SI, and this has been used for some time now, okay? For example, without units, a number can be meaningless or confusing if somebody said, well, how much water did you drink today? And I said, one. Well, that would not be very helpful, would it? Is that 1 glass? Is that 1 gallon? Is that 1 milliliter, right? So it turns out units are very important, okay? So the base units for SI are, for length, these are the properties or dimensions, okay? And the symbol or the unit itself is here, and the symbols are there, right? So for length, it's meter. For mass, it's kilograms. For time, it's seconds. And this is where most of our world is going to be, okay? We're not going to be doing much with electric currents, maybe none. We'll be doing none with luminosity. Really, I'm going to put that out. Look, we're not doing anything with that. Kelvins, we are going to need kelvins, okay? And we're going to need moles as well. So these are the base units. The symbols are here. We can always look those up. Those are the base units for those particular dimensions. Now, important prefixes, these are also things we can look up, are as follows. Centimeter, this is the same thing as 1 over 100. You can see why, right? That's what that means. This is the same thing as 1 over 1,000. Micro is the same thing as 1 over a million, right? You can see this is why it's important to use scientific notation, right? Because we eventually are going to be able to access some really awkward numbers. It's a very awkward number right there, unless you simply use the word micro, right? The symbol for that that's a mu. It's a Greek letter mu. That's my version of a mu. This, of course, is better, but you're gonna have to be able to read someone else's mu, right? M is a little bit easier to read. C and D are what things you're familiar with, right? So these are the prefixes, so that we can talk about really big or really small units. Okay? And then here's some big ones. The previous ones, these were all small, right? These were all negatives. Here's some big ones. Kilo is 1,000. Mega is 1,000,000. Giga is 1,000,000,000. And tera is 1,000,000,000,000. Okay? So now let's probe these a little bit more. The common base units for length is the meter, as we know. The meter was originally intended to be 1/10,000,000th of the distance from the North Pole to the equator. Pretty funny, huh? 1/10,000,000th of the distance from the North Pole to the equator. That was the original intention. A meter is now defined as the distance light travels in a vacuum in this many seconds. Or that many fractions of a second, right? A meter is about 3 inches longer than a yard. And we've got some other ways of thinking about this. There's about 0.93 miles in a kilometer in 1,000 meters. There's about 1,609 meters in 1 mile. We've got different ways of thinking about that. And we've got one more exact dimension, and that is 2.54 centimeters is equal to 1 inch. So we'll get that more later. Like right here, okay? 1 inch is equal to 2.54 centimeters exactly, by the way, okay? It's not 3 sig figs, it's exact. And this is not necessarily exact, but this one is exact. A meter, a yard is a little bit smaller. Can you see that? A centimeter is 1/100th of a meter. And an inch is 1/36 of a yard. So there's just some relative pictures to get you for you to get a sense of how big a meter is compared to a yard and a centimeter and so on. Okay, now the common base units for mass is the kilogram. A kilogram was originally defined as the mass of 1 liter of water, and that's really very close to true now. It is now defined by a particular cylinder of platinum and iridium alloy, which is kept in France, of all places. 1 kilogram is about 2.2 grams. Here's a replica of the thing it's held in France. And can you see you've got 2 bell jars here? Can you see you've got bell jar here and bell jar 1? Like basically, we're going to make sure that this thing is not affected by oxygen, right? That's what that's all about. All right, so in that platinum iridium alloy is in there, and that's what weighs 1 kilogram. Now, this is just a replica, but it's held at NIST, which is the National Institute of Standards and Technology, and it turns out it's our standard. Okay, the base units for temperature is kelvins. There's no word or symbol used in Kelvin, right? The degrees, Celsius does use the symbol. There should not be a space here. That's a misprint. And Celsius degrees are the same magnitude as those as Kelvin, but they're off by that many degrees, right? So 0 degrees Celsius is very cold, right? That's freezing point of water. But even though it's the freezing point of water, it's still 206. Sounds high, right? 273 kelvins, but that's what it is. 273 kelvins. And then the boiling point of water is 100 degrees Celsius, and that's 373.15 kelvins. All right. The base units for time are seconds. Smaller and larger time intervals can be expressed with the appropriate prefixes. Where am I here? And we can also use hours and days. All right. So now we have some derived SI units, and that is unit volume, for example, is length cubed, right? Length cubed is equal to volume. So the standard SI unit for volume is the cubic meter, right? Which is a lot of liters. I think it's about 1,000 liters, but it's a lot, right? So, but that's the standard SI unit for volume. It's the cubic meter. And other units for volume that we use frequently are liters and milliliters, right? So a cubic centimeter is equal to 1 mil by definition. 1 mil by definition. So, and you can see how you can get from cubic meters to cubic centimeters, right? It's just a conversion. And then from mils to liters, that's another conversion, which we'll be doing a lot this semester, okay? Now, just to give a visual picture of how of what these dimensions are, 1 liter is 1 cubic decimeter. That's 1 liter. And here's 1 cubic meter. So yeah, it looks like it's, what's that? 10 times 10 is 100 times 10 is 1,000. So that's right. There's 1,000 liters in 1 cubic meter. It's pretty big. Okay? 1 cubic centimeter, that's the same picture right there. It's just blown up a little bit. Is about it is exactly 1 milliliter, and then a dime is about 1.8 centimeters. This is just to give you a sense of how big these things are, right? All right, so let's move on to density. Now, here's another derived unit. Density is mass divided by volume, right? This is an intensive property, and the density of a substance is the ratio of the mass in the volume. We're going to use this a lot, density. The standard SI unit for density is kilograms per cubic meter, although as chemists we oftentimes say grams per cubic centimeter, which is not the same thing. Not the same thing at all. But that's even though this is the SI unit for it, this is going to be the most common one that we use. We can convert between those very easily, so not something that you should worry about too much. All right, and so that's it for this section 1.4. In section 1.4, we're talking about measurements. We talked about numbers not much. We talked about units a lot. and the different dimensions of units, length, mass, temperature, and so on. We did not talk about uncertainty of measurement. We're coming up to that very soon.